and connectors. And yeah, it looks like we are live. So hello everybody, and welcome to another session of our Sussex Vision seminar series, always within the Worldwide Neuro Initiative. I'm George Kafedis, a former master's student in Thomas Euler's lab, and relatively speaking, newly arrived PhD student with Tom Baden. As your host for today, I would like to once again begin by thanking Tim Vogels and Panos Bozelos for putting forward this very initiative towards a greener and much more accessible seminar world. And of course, having said that, please allow me to get back to the reason we all gathered here for today and introduce our guest from University of Cambridge, Professor Simon Laughlin. Following a bachelor degree in zoology from Cambridge, he then moved for his PhD in neurobiology to Canberra in Australia, where he worked with Alan Horridge on visual processing in insects, and more specifically, I think, dragonflies and bees. During his time there and in close interaction with mathematicians, physicists, and engineers, he spearheaded the application of information theory on neural coding, acquired data on natural image statistics, and according to Horridge himself, virtually dealt with all the signal-to-noise ratio stuff. Following postdoctoral years at Yale and Berlin universities with William Miller and Randolph Menzel respectively, he then returned in 1984 to the zoology department of Cambridge, where he has been located ever since, and nowadays is holding the title of Emeritus Professor of Neurobiology. Deservedly, he is best known for his pioneering and seminal work on relating through basic biophysics energy usage to neural performance and what that implies for neural design and evolution. A fellow of the Royal Society since 2000, recipient of many personal awards and co-author with Peter Sterling of the award-winning book Principles of Neural Design, it is with great pleasure that I'm leaving the stage for him, Professor Simon Laughlin, for a talk entitled Receptor Costs Determine Retinal Design. So without any further ado from my side, please all welcome Professor Laughlin. The stage is all yours. Right. And Simon, yeah, you can begin by screen sharing or...
Okay. Can people all see my screen?
Yes, though we still see the presenters mode. You can swap it from the top left corner again, like for from the display settings. Now we cannot see it again. Did you stop screen sharing? I think
right. I didn't put it back in. I didn't leave presenters mode.
Okay, right now we cannot even see your screen sharing. So I think you also stopped that, right?
I've stopped screen sharing, yes.
Okay, so you can restart it if you wish, and we can figure it out together.
Okay, so here we are. This worked before. Share PowerPoint.
Great. Now try going into presentation mode. Yeah, and now if you see at the top left corner, yeah.
Oh, right,
settings.
okay. There we go.
Excellent, yeah. So we are good to go.
Okay, well, thank you very much for inviting me, George, and thanks in particular to Sussex Vision Group and to Worldwide Neuro for giving me the opportunity to speak to such a worldwide audience. It's a first time for me. So I'm going to return to my roots in actually to work which dates back to my PhD, looking at eye design. But in this particular case, I'm going to factor in some of the insights that I got looking at costs. Now, receptors are very costly, photoreceptors are very costly, And they, for example, in a blowfly, they're responsible for something like 6% of the resting energy consumption. And they occupy, as we will see, quite a considerable amount of volume. The retina of a blowfly, of its two eyes, which includes the optics, that accounts for something like 15% of the body weight. So insects invest very heavily in eyes, and they're especially heavily in photoreceptors. And in view of this, Francisco Hernandez Heras and I decided to take a new approach to understanding eye design. And we asked a question that anybody who's built an imaging system on a small budget will have asked. And that is, how much of my small budget should I give to the optics, which forms the image, and how much should I give to the receptors, the sensors, which actually capture the image? Is there some optimum resource allocation that will maximize the performance of the whole system? And short answer is that yes, there is, but to demonstrate this to you and for you to understand what I'm on about, we have to start off with a few basics about eye design and how performance of an eye depends on investment in its particular components. So we'll start with Land and Nielsen's book on animal eyes, and they have a chapter called What Makes a Good Eye. And in that chapter, they explain that 3 factors make a good eye. So the first is when the lens focuses light onto the retina, the parallel rays from a point do not form a single point on the image plane. They're spread out to form this point spread. A second factor is that there's a discrete spacing of the receptors. And the third factor is that there is photon noise introduced when photoreceptors absorb photons, because that's a stochastic process. So let's just run through these 3 constraints on the performance of an eye. So first of all, the angle between photoreceptors. Well, in a simple lens eye, that simply depends on the focal length and the angular diameter of the photoreceptor aperture. So the angle is the aperture of the photoreceptor divided by photoreceptors determines your ability to resolve, whether you measure that by your highest or by 2-point resolution. Okay, so that's, and they have an interreceptor spacing, which is now the spacing between the optical units. Lenses on the lens on each ommatidium of the eye, which is where all of these axes eventually would converge, and the angle is the diameter of the optical radius. And it's obvious that if both these eye types, that if you make a larger radius or a larger focal length, a larger eye, you'll
Okay, probably something happened with our guest's internet connection because Simon, you are muted again. Can you hear me? Let me unmute you. You are muted, Simon.
Okay, I'll unmute.
Great. So I think your connection might be a little bit shaky, unfortunately. So what I would suggest is again, like start screen sharing.
Wait a moment.
Yeah, sure. Take your time.
Right, here we go. So I think I've stopped screen sharing, right?
Yeah, so try restarting it, please.
I mean, I've had a lot of problems with our internet recently, and everybody in our street has been having problems. I'm sorry.
Yeah, I can imagine. No worries. Like what I would suggest just for the beginning, like maybe start screen sharing, and what we can do is you will switch off your own video.
Yeah, I can do that. Yeah.
Great. So let's try that.
I probably only look like a crazy puppet, very distracted. Yeah. Okay, so let's go to screen share. You got that?
Yes. Try again presenters and slide presentation mode.
Yeah.
Swap the two displays again, please. Like from the top left corner. Great. And
yeah, I've done that.
would you like to try like switching off your video for now? Like maybe.
I think I would have to do that before I go into the. Oh no, I've got it up here. Stop video.
Great. So hopefully now all your internet will be devoted, you know, to your voice and your slide presentation.
Yeah. Okay.
Let's try it like that and see how it goes.
So sorry about that, folks. So this is the constraint of interreceptor spacing. As you can see, it pixelates the image and has an obvious deleterious effect on image quality. And you want to minimize this angle between photoreceptors, delta phi. The second constraint is the point spread function. And this diagram just shows how the point spread function blurs the image. That it basically takes bright light from the bright points and spreads it to the dark points. So it reduces image contrast. And as these line scans through the image show, it removes fine detail from the image. The final constraint, so that's the point spread function. The final constraint is noise from photon absorption, which just makes everything more difficult to see. Okay, so by investing more in optics and photoreceptors, an animal can improve the quality of the captured image by reducing what are inviolable optical, geometrical, and cell biological constraints on delta phi, the point spread function, and noise. And I thought the best way to illustrate this was to look at some really cool insects which have specialized to improve the performance of their eye for particular tasks by investing very heavily in optics and in photoreceptors. And the first example is the predatory robber fly, Holocephala, which has been studied in a really nice paper by Trevor Wardle and Paloma Gonzalez-Belido and Dukla Stavanger and others, where they looked at the behavior of this fly and also looked at the specialization of its eye. So the robber fly is very small, its head's about 2 millimeters across, and it detects prey at about the distance of 28 centimeters, which doesn't seem very far, but its prey are also very small. And then it flies up and intercepts them. And in order to locate and track its prey, it has a fovea, a small area on its compound eye where the facets are very, very large. And there's a section through the fovea shown here. And you can see that the layer of the compound eye, which constitutes the optics, which is the lens plus the crystalline cone through which it focuses light down onto the photoreceptors, that volume of optics is greatly increased. And in fact, the volume of the eye in this region of the fovea is large. The lenses are very large. They're the largest known in any insect at the moment. And their focal lengths are long. They're about focal distance from the top of the lens down to the focal plane is about 170 microns. The angle between receptors is very small, and that means that with a large D and a small angle, the optical radius is 15 millimeters. And about 20% of the eye volume is used to monitor about 1.1% of visual space. So this is a huge investment, and largely in the optics. So what does it gain from that? Well, there are two fundamental limits to the angular sensitivity of a photoreceptor. The first is diffraction at the lens aperture, which generates an airy disk, which has a half width of lambda wavelength of light divided by d. So if you increase lens diameter, you narrow this component, the airy disk, of the blur function. The second constraint is the angle subtended by the entrance aperture of the photoreceptor's waveguide, the so-called, which in these flies is called a rhabdomere, the diameter of the rhabdomere. And this angle is simply the focal length, as we've seen, divided by the, no, it should be the diameter of the rhabdome divided by the focal length. Written this talk in rather a hurry. So if you make the focal length longer, you get a small, this angle reduces. And these two effects combine together in a very complicated way, because this is diffraction coupling of a waveguide to, this is a coupling of a waveguide to a diffraction pattern. And there's a very simple approximation due to Alan Snyder, which is you assume that these two functions are Gaussian, and you simply sum them together. And it works moderately well for some insects, but is complete rubbish for others. But for the basis of a general study, this is the best we've got. But it emphasizes the point that when you invest in optics, you reduce the effects of blur by narrowing the angular sensitivity. So now what happens when you invest in photoreceptors? Well, the animals, in the animal kingdom, the largest investments in photoreceptors in terms of the volume that they occupy in an eye is probably made by dragonflies. And this is the dragonfly I did my PhD on, Hemicordulia tau. And you can see in this photograph here that its eye is divided into a dorsal area, which looks at the sky, and a ventral area, which looks at the ground. And in the dorsal area, the light guides formed by individual photoreceptors, the equivalent of the outer segments that capture light, are 800 microns long. And this compares with, this is 40 times longer than a human cone outer segment. It's about 3 times longer than the longest known outer segments, which are in deep sea fish rods, and it's a bit longer than deep sea squid photoreceptors. So this goes against what you learn in the textbooks, that animals have long photoreceptors to get more photons, and therefore this is a specialization for vision in dim light. And in fact, the longest photoreceptors known in the animal kingdom are in the dorsal fovea, the part of the dorsal eye which is used for tracking objects, in the dragonfly Sympetrum. And they are 1.1 millimeters long. And this dorsal fovea has been studied in considerable detail by Dan Erik Nielsen and Thomas Labhart. And the function of the fovea has been studied by, in particular in the lab of Anthony Leonardo, previously at Genelia Farm, and they showed by amazing techniques for tracking single dragonflies intercepting prey, that when a dragonfly first sees a prey, it flies up towards it and it locks its fovea onto its prey target. And as it approaches the prey, it moves its head to keep it centered, the fovea centered on the target, and then adjusts the body to align with the head. And it's using really fancy control systems. So we know exactly what this fovea is being used for in behavior. And Dan Erik Nielsen and Thomas Labhart showed that it has unusually narrow so they measured the interomotidial angle and facet diameter across the eye, and in the region of the fovea, which is the blue part here, then the interomotidial angles are very small to give you very good spatial resolution, and the facets are very large, and so are their focal lengths to give you a very narrow blur circle. And in addition, the photoreceptors in the fovea are greatly elongated. And this turns out that this doesn't look like a big deal when you look at it in angular space, but because the ommatidial density is very high in the fovea, the area of retina taken up by the fovea is quite large. So again, this is a big investment for the dragonfly. So why has it bothered to make such long rhabdomeres? What does a strictly diurnal animal gain from having such long photoreceptors? And the answer to this, as Laughlin and Nielsen pointed out, is that it reduces a cell biological constraint on photoreceptor signal-to-noise ratio. And this cell biological constraint is the fact that photons are transduced by microvilli. These are little tubes of membrane which contain the photopigment shown in cross-section here. And each microvillus acts as an independent unit that responds to a photon by recruiting its phototransduction machinery to produce an all or nothing event, rather like a mini action potential called a quantum bump. And each microvillus can only transduce one photon at a time, and the process of phototransduction from absorption here to the formation of the bump and then the recovery, the resetting of the microvillus, takes some time, between 10 to 50 milliseconds. And what this means is that at very high light levels, many of the microvilli are in this refractory phase and are unable to transduce photons. And you can see that this effect in blowfly photoreceptors. In this study I did with John Anderson, we used noise analysis to estimate the rate at which photoreceptors were transducing photons, and we plotted this against the rate at which they were absorbing photons calibrated from quantum bumps. And what you can see is that at high light levels, the rate of photon transduction falls below the rate of absorption. And this is due to two effects. One is an intracellular pupil, which brings up pigment granules to attenuate the light, and the other is the saturation of transduction units. And in fact, the pupil is mitigating the constraint imposed by transduction units. And this was shown by Joe Howard back in the 1980s, where we took a blowfly photoreceptor and we measured the signal-to-noise ratio in the wild type as a function of the light intensity, photons per second coming in per receptor per second. And in full daylight, you can see that it's operating at this level here. Then if you have a white-eyed mutant, then it has no intracellular pupil, so it's unable to attenuate the light. And the white-eyed mutant response signal-to-noise ratio goes up and up and up, reaches a peak, and then comes crashing down when you get to higher photon absorption rates, because the transduction units have saturated. And you can fit this curve here quite well with a binomial distribution, which is what you expect of saturation. And when you do that, you find that the maximum signal-to-noise ratio is proportional to the number of square root of the number of microvilli divided by 4. So the number of microvilli in that rhabdomere determine the maximum signal-to-noise ratio that you can get. And the action of the pupil is to prevent you from getting to saturation and to hold you close to this maximum signal-to-noise ratio. So when we model this constraint, we model the benefit of having a longer photoreceptor is that if it has a a constant cross-section, the number of microvilli increases in proportion to the length of the photoreceptor, and that sets the transduction unit limit to signal-to-noise ratio. And we assume that in the eyes that we're going to model, that they have some sort of mechanism for holding the photoreceptor close to this optimum. So this is the benefit of a long photoreceptor. But there's a puzzle. And the puzzle is, if you go to the ventral eye region here, you still have very long photoreceptors. They're 500 microns or so long. And you really can't explain that as an adaptation for detecting very small targets in a fovea. There must be some other advantages of having these long photoreceptors. And in fact, having long photoreceptors outside of a foveal region is very common. This is the praying mantis, where Horridge and Duelli took sections through and showed that in the region of the fovea, which is forward-looking, you've got large lenses, long focal lengths, but also very long photoreceptors. And as you move away, the investment in optics goes down, this band gets narrower, and so does the investment in photoreceptors. They get shorter. And Sam Rossell showed that there's a very neat covariation between the length of photoreceptors plotted here as one moves across the retina with a peak close to the fovea and the lens diameter d. These covary. And this led Fran and I to the idea that maybe the investment in photoreceptors, which depends on L, is matched to the investment in optics, which depends on D. And in fact, this correlation between photoreceptor length and lens diameter, and also interomotidial angle, is widespread among insects. You can observe it very easily in slides, but photoreceptor lengths have not been measured very often in insect compound eyes and related to lens diameter and interomotidial angle. There's stacks of studies out there which look at resolving power in terms of diameter and interoceptor angle, but very few of them correlate these with or also measure photoreceptor length. And so the data that we were able to mine from the literature, which is these points here, is really quite limited. But you can see that there's a very nice trend, and that holocephala, with its very heavy investment of optics and relatively short photoreceptors, is an anomaly. And you can explain the short photoreceptors because the head is only about half a millimeter deep. And so photoreceptors of 500 microns simply wouldn't fit inside the head. So this reminds us that there are other constraints. Nonetheless, there is this systematic trend, and it's a general trend. So we set out to test this hypothesis by calculating investments and then determining their effects on performance. And the method for calculating investments is really very simple. We assume that in a small region of the eye is locally spherical with an optical radius defined by d and delta phi. The investment in the optics then is the volume of this outer shell of depth f prime, where f prime is the focal distance from the top of the lens down to the focal plane, the outer front surface of the lens, the focal plane. The investment in the optics is the volume of this shell here from the focal plane down to the bottom of the photoreceptors is determined by this shell here, which has a depth of the length of the photoreceptor. And it's very easy to calculate these from the volume formulae for the volumes of the sphere. I won't grind through the formulae, but note that these formulae only contain three variables, which are the optical radius, the length of the photoreceptor, and this distance here, f prime. And if you assume that f, the focal length of the photoreceptor, is that the system has a constant f ratio, then diameter also gives you focal length, and it's been found empirically, as one might expect from very simple theory, that in fact this distance here, the focal distance, is the focal length times the refractive index of the internal medium. And what this means is that if I give you V total, lens diameter, and L, you can determine delta phi, the investment in optics, and the investment in photoreceptors. And we know that D and F determine delta rho, and L determines the signal to noise ratio. So here we have all three of our quality factors, just related to the investments in volume of optics and volume of photoreceptors. And we also know, that's explained here, how changing these investments will improve or decrease, will improve performance or decrease performance. So we can now examine the trade-offs. But you might say, what about photoreceptor energy costs? I've said that energy is very costly, and yet the optics are relatively inert. And in order to get an estimate of the extra cost of energy, we made a very simple and probably very foolhardy, we took a very simple approach, which contains a lot of problems, but it's, at the moment, it's the only thing you can do. So our cost of volume is, our volume cost, if you assume constant density, is also a cost of mass. And when a flying insect, its oxygen consumption in flight is very high, so its metabolic rate in flight is very high, and a part of that metabolic rate is devoted to carrying the eye around. So it's going to be proportional to the mass of the photoreceptors and the mass of the optics. And this gives you a method of converting energy, which is from metabolic rate, into mass and therefore volume. So we can come up with an extra energy cost due to electrical currents in photoreceptors, which increases with the number of microvilli in proportion to the microvilli, because that's the number of transduction units consuming energy. So the total cost is going to be the eye volume plus this energy factor, which is the number of microvilli multiplied by this conversion factor that converts, which is in cubic microns per microvillus. And this is calculated from the energy consumption of a single microvillus, which has actually been estimated in some quite accurately in flies, and measurements of energy per unit volume and therefore mass in flying insects. This is a very fraught calculation because in fact it depends on how much of the day a microvillus is illuminated and how much of the day an insect spends in flight. And it's species specific because it's going to depend on the flight mechanics and body mass of the insect as well. But in fly prolifera, we can make a very rough estimate, and this factor seems to vary from could vary between 0.05 and 0.32, depending on how much the fly flies and how much during the day and what the day length is. But that's our method of getting an energy discount factor. And it's not a very good method, but at least it enables you to show how the design of the eye will change with photoreceptor energy costs, and we can get it into the right ballpark. And I'll just say in passing that this conversion, actually, I think David O'Carroll and I first discussed it years ago when we measured the masses of eyes, but it's since been, it was independently hit upon by people working on weapons in beetles. So beetles, some species of stag beetle, carry huge horns on their head, which are very heavy, and they wanted to work out what the cost to the beetle was of this. So they used this method here to convert the mass of the horn into an energy consumption. Okay, so this is our method for taking account of energy costs of photoreceptors. Now let's look at our trade-off. So just to recap on what the trade-off is, if you invest more in photoreceptors, you will get a more blurred image. So the compound eye is looking at this image here, and both of these configurations have equal total volumes. And this emphasizes that the volume on the outside, towards the outside of a sphere, equal volume on the inside of the sphere and outside of the sphere, involve very different distances from the center. And so it's difficult to believe that this really is the same volume of that. But if you sit down with a piece of paper, you can show that in fact that it is. And so if you invest very heavily in photoreceptors, you must invest less in optics. So you get a very blurry image, but there's not much noise. And the opposite happens when you go for optics. Now, it's very difficult to look at these two images and decide which one is really best. And so we need to, when we set up this trade-off, we need some method of evaluating the performance of the quality of the image and therefore the performance of the eye. And so we used a model, a method developed by Hans van Hateren for calculating information rates in bits per solid angle per second based on those quality factors that we've deduced, delta phi, del rho, and the signal to noise ratio. And we modeled two similar types of apposition eye, of compound eye. The apposition eye, in which the lens drives a group of photoreceptors which contribute microvilli to a single waveguide. And the others are the neural superposition eyes of particular flies, in which the waveguides of the photoreceptors, entrance apertures, are distributed across the image plane. So each one is looking out through the lens in a different direction, but the angles between photoreceptors within an ommatidium are the same as the angles between ommatidia. So they're always adjacent photoreceptors which align, and the axons from those aligning photoreceptors that align are brought together to a single point at the first optic neuropile. So you get a neural superposition of the image that they've collected, and that's the neural superposition eye. And the advantage of the neural superposition eye is that it collects more light, and also, as we show here, that you get more microvilli per unit length. So this constant B that relates length to numbers of microvilli is in fact roughly twice as large in the open rhabdome than it is in the fused rhabdome, because each one of these segments here is roughly equivalent to one of those. And there are 3 of these and 6 of these outer rhabdomes here. So in everything that follows, you'll see sets occurs for neural superposition and apposition eyes, and that's what they mean. And so we go now and we look at image capture. We're considering in the Van Hateren method, one considers an image which has a certain intensity distribution in space, and that follows natural scene statistics, 1/f squared. And this image jitters backwards and forwards, so that when it's viewed by a single ommatidium, the photoreceptors in a single ommatidium, the photoreceptors get an optical signal which moves up and down with the jitter of the image. And the point of using jittery image is that it actually tends to decorrelate the spatial frequencies in here from and the temporal frequencies, which is what you need in information theory. Then this intensity signal in the photoreceptor is transduced into an electrical signal, and this adds photon noise, which is ultimately limited by the length of the photoreceptor, as we've seen. And Hans van Hateren came up with this hideous looking formula, which, taking these quality factors, gives you an information rate. And I don't have the time or inclination to ride through the formulae, but if anybody wants to discuss it, we can come back to this slide. And this model then allows us to address our question: how does performance change when resources are transferred between photoreceptor optics? And the way in which we do this is that we fix the volume invested in the eye, and we consider different energy surcharges. And for each volume, V total, we pick pairs of combinations of pairs of lens diameters and receptor lengths, which fit into which can be accommodated in an eye of that particular volume. And each DL pair specifies a particular eye configuration, and as we've seen, specifies the quality factors. So for each DL pair, we can calculate the information capacity as we vary, and so we can plot that out as you vary D and you can vary L, you see how the information capacity varies. And what you can see is that this surface is the performance surface that covers the complete design space of all possible configurations of eye of this particular volume with this particular geometry. And you can see that the performance surface is actually flat topped and elongated. And when you increase the energies, and there's an optimum around here somewhere where efficiency is maximum, and when you increase the energy surcharge, the optimum photoreceptor gets shorter in length, which is what you would expect. But the interesting thing about this performance surface is it's actually very smooth and flat on the top, on its top. And this is very more clearly seen by looking at contour plots. So here are contour plots at 3 different energy surcharges. And this red area here, and you can see that there's an optimum here and here and here. And that sits in this red area, which is a robust high performance zone in which efficiency is greater than 95%. Now, this is very bad news for modelers who search for optima, because they're going to be very messy, as you will see. But it's great news for insects, because what this means is you can vary the parameters. You can vary D and L within this high performance zone for a particular task, getting larger D or larger L, and yet lose very little capability for general purpose vision, which is what information theory gives you. And you'll see that the shapes of the surface depend on the energy surcharge factor, that as you increase when the energy surcharge factor is low, you want the longest possible photoreceptor. And as you increase the energy surcharge, the high performance zone elongates, and the optimum point of high maximum efficiency moves to lower lengths, and eventually at the highest energy surcharge factors, then you can see that the performance zone has also contracted to shorter photoreceptors. Now, in order then so this means for any particular eye investment, we can work out what is the optimum combination of investment in optics and investment in photoreceptors, which maximizes efficiency, and how sensitive is the system to deviations away from the optimum. And one can do that for different energy surcharge factors. So now we can perform this procedure for over a range of total investments to see how these D and L scale, and in particular L scales for total investment, and therefore how L changes with the acuity of the eye, and how this shows whether L is matched to total investment and therefore matched to the optics. And what we find is that as you increase the total investment, the specific volume of the eye increases. That's the volume of eye per unit solid angle. And the optimum specific investment decreases with energy. The optimum investment in photoreceptor length decreases with energy surcharge. And you can see there's a bit of instability in the model because we're in this very flat zone. But nonetheless, there are clear limits between the 2 energy surcharge factors, which are our lowest and highest estimates. And these spots are data points that we mined from the literature, showing variety of species. That's Calliphera's frontal eye, that is Calliphera's lateral eye. These are the two values for musca. And down here are a whole load of small flies. And you can see that these points fall within the zone of high efficiency. And also you can see that matching the optics captures the general trend that you see in real eyes. But of course, you can't see very well what's going on down here. So if we put it on a log plot, you can now see these smaller eyes. That's Drosophila there. That I think is, that might be holocephala. And haven't gone out to very long lab domes not to have holocephala here. But you can see that the model captures the trend of the data. So it looks as if this lengthening of rhabdomeres with increase in lens diameter and increase in acuity that you observe in eyes is in fact representing efficient allocation of resources for general purpose vision, and is not simply a specialization for it is a specialization for high signal to noise ratio, but it's not specialized for a task which is particularly demanding of high signal to noise ratio. It's worthwhile investing in that to make efficient use of your entire investment. When you look at the apposition eyes, again, these are the theory curves for low and high energy surcharge. And again, you see this instability in the theoretical curve, which is skating around on the top of that flat high performance zone. And you can see here is data from 3 different apposition eyes, Sympetrum and Tenodera, which we've already seen come from Labhart and Nielsen, and Tenodera from Sam Russell and Horridge and Durelli. And this is the honeybee, where the data comes from a paper by Menzel and Stavinger and Tinbergen, I think. And you can see again that there is a definite trend for the most efficient photoreceptor length to increase with specific volume. And this trend is kind of captured by the model. So the model also tells us how much of what percentage of the total investment should be in the photoreceptors and therefore in the optics. And again, you see that the percentage tends to increase in theory with specific volume percentage in the photoreceptors. And this trend is captured by and this trend is demonstrated by, same trend is shown in the empirical data, both in neural superposition and in apposition eyes, but the fit isn't terribly good. And again, that's because you have this flat surface on the top, which militates against a very good fit of an optimization model to observe data. Plus the fact that you have a robust zone, so there's plenty of, so that the evolution is free to wander around with different eye configurations without losing too much information. Finally, for aficionados who work on compound eyes, there is a factor called the eye parameter, which takes into account undersampling. So the eye parameter invented by Alan Snyder is the diameter of the lens times the interomotidial angle. Now, at the diffraction limit, when the interomotidial angle is set to the diffraction limit, this turns out, P turns out to be half the wavelength, turns out to be the wavelength of light divided by a factor of 2, which is 0.25 here at the diffraction limit. P is 0.25. And in apposition eyes and neural superposition eyes, only the fovea of Tenodera and the fovea of Sympetrum get close to this diffraction limit. Most eyes have a P which is quite a bit larger than 0.25, and this P, this means that they've got much larger lenses with much better diffraction limited resolving power than there can be catered and much larger interomotidial angles, which means that the interomotidial angles are too wide to retrieve all of the spatial information provided by the spatial resolving power of the lens. And as has been observed by many people before, the majority of insects undersample. They have a P quite a bit lower than higher than the diffraction limit. And our model predicts that the P should not approach the diffraction limit for efficiency, but many values of P are considerably larger than are predicted by our model. And it's worth noting that P varies enormously within a single eye. So there's lots of factors deciding the exact balance between diameter of receptors and interomotidial angles. And so there's lots of variation, but within those variations, as we've seen, there is a trend for photoreceptor length to get larger as predicted by our model. So we conclude that we have quite good evidence for there being a matching, that efficient resource allocation can explain why, in general, insects have long photoreceptors, and the length of the photoreceptor increases with the acuity of the eye. But why are they so much longer than photoreceptors in simple eyes? Well, Fran went back and used this equivalence of photoreceptors of, simple and compound eyes, where again you got D and delta phi, and R and delta phi, and D, and focal length here. And he reconfigured the model for a simple eye, a very simple eye with a simple lens, and worked out what the optimum photoreceptor lengths were. So these are the optimum photoreceptor lengths as a function of investment in the eye in specific volume. And here are the curves for Diptera, for flies, with a low energy surcharge and a high energy surcharge. And here are the equivalent curves for a simple eye. And you can see that efficient resource allocation can account for the fact that simple eyes have much shorter photoreceptors. And in fact, this difference extends over the full range of eye volumes that we encounter in insects, out to about 1 × 10⁻¹1 cubic microns per steradian, where the equivalent curves for a neural superposition eye and a simple eye are separated by a factor of about approaching a log unit. And in both cases, the energy surcharge factor decreases the length of the optimum photoreceptor. And of course, this model predicts that in a simple eye, if you invest more in optics, then you should have longer photoreceptors. And observations in jumping spiders suggest that that is indeed the case. But here, jumping spiders have 4 different eyes, and one of them, the frontal eye, pair of frontal eyes have very large lenses with long focal lengths, so they invest heavily in optics, and they have longer photoreceptors shown here than the other eyes, which invest less in optics. And in fact, you can see that the photoreceptor length tends to decrease with the investment in optics. So there's every indication, or at least there's one indication, that in fact efficient resource allocation can explain the short photoreceptors in simple eyes. Finally, our model confirms what is already well known, that the compound eye is very inefficient. The compound eyes are very inefficient. These are the information rates as a function of total investment, calculated for calculated using our model. for simple eyes with low and high energy surcharges, and neural superposition eyes, and also apposition eyes. And you can see that, say, at the size of eye of sympetrum, which is here, then the efficiency is about 100 times less than in a high energy surcharge simple eye. And if the energy surcharge is very low, the efficiency is in fact 10,000 times less, which was first of all pointed out, this inefficiency was first of all pointed out by Kuno-Kirschfeld in this, who constructed this famous diagram showing how large your eye would have to be if it was a compound eye. And the reason is very simple, that if you want to double the resolution of a simple eye, as you can see, you just double the focal length and the size of the lens. And that means the receptor spacing halves and the diffraction limit halves, and their two are matched. But if you want to do the same in a compound eye, then you need to double the size of the lenses to reduce the diffraction limit, and that doubles the size of the eye, but you then have to halve the interomatidial angle, so you have to double the size of the eye again and have twice as many lenses. And so you get this massive inefficiency. So, well, after all of this, what have we learned? Well, we've taken a new approach to understanding eye design by considering the costs of investing in optics and photoreceptors and examining the effects of resource allocation, transferring investment between optics and photoreceptors. And we find that the total investment in the eye can be divided, can be allocated to improve the eye's overall performance. And there's an optimum, and also there's a robust zone. And this favors long photoreceptors in compound eyes. Efficient investment depends on the cost-benefit relationships of both optics and photoreceptors, which is why simple eyes and compound eyes are different, and why the energy surcharge tends to reduce investment in photoreceptors. And so when compound eye optics is less efficient than simple eye optics, more is invested in photoreceptors. And this means that optical inefficiency of compound eyes explains a fact which is so obvious that actually it really hasn't been remarked upon very much. And that is fast-flying diurnal insects have the world's longest photoreceptors. And in general, the photoreceptors in fast-flying insects compound eyes are much, much larger than in vertebrate eyes. But much remains to be learned. This is just a very simplified model where we've made lots of simplifying assumptions to establish proof of principle, really. And the first is that the eyes operate in full daylight. Well, we could relax this to examine designs for different light levels. And one of the ways in which one would do this is to relax the assumption that the F number is kept constant. And this allows you to trade sensitivity for acuity within the optics, within the constraint of cost. We could disregard exponential absorption. We've disregarded exponential absorption in rhabdomeres and gone for vision in high light. Of course, at low light levels, you need to relax that and include exponential absorption. And in fact, Fran has already done this for a model of polarization sensitivity in photoreceptors that we published some time ago. We've assumed constant photoreceptor cross-section. This can be relaxed to adjust the width of the rhabdomere and to make the best use of microvilli along the length of the rhabdomere. And again, this can all be done within the function, within the trade-offs between performance and cost, which we've been able to set up by estimating volumes. And I'll just say in passing that although we've estimated volumes, new techniques for measuring three-dimensional tissue structure, particularly new imaging techniques, X-ray imaging techniques, are going to make it possible to measure volumes invested quite accurately with much less effort previously. And so this, this cost-benefit approach might very well take off. We assumed that the temporal parameters, image speed and photoreceptor response dynamics, were the same, and one can relax these to investigate the effects of photoreceptor response dynamics and image speed. And we've also assumed that energy consumption for microvillus is constant across species. But in fact, we have to relax this because some species have faster responding photoreceptors with higher energy costs per microvillus, and maybe spatial and temporal coding co-vary to improve efficiency. And finally, of course, one needn't use bit rate as a measure of performance. One could apply this same cost-benefit approach to, say, the detection and tracking of small targets. And so all of these possibilities, in fact, can be investigated within this cost-benefit framework that we've started to construct. And so really it only remains for me to say, thank you, Fran. This actually was Fran's master's thesis originally, and over the years we kind of worked it up a bit, and Fran is now working in the Champalamo Center in Lisbon on schooling in zebrafish. But we're still plugging away at this project, and we hope to have a manuscript out by Easter. So, okay, over to you for questions, and thank you very much for listening.
Thank you very much, Simon, for this enlightening talk. I mean, lots to unpack, and I believe you can now try to switch on your video. It was quite sad that we couldn't see you while you were giving us the presentation, but nevertheless, at least the audio quality became quite stable throughout. So there are already a couple of questions on the chat, and you have definitely scratched the surface of most of them. I just want to remind to the audience that you can either type your questions there or wait for the post-talk informal discussion that will soon follow. Like, we will shortly also post the Zoom room link that we are currently seated in, so you can join us. A lot of people are already congratulating you on the YouTube chat. I assume you don't have it open, and I will begin with the questions. The first one is from Bobbert Joe, and he asks, what's the absorption length of an insect photoreceptor? In vertebrates, I seem to remember 50 micrometers or so. In that case, a millimeter long photoreceptor wouldn't see any light near the bottom.
That's a very good question. Yes, so the absorption coefficient in an insect photoreceptor is, as I remember it, something like 0.08 per micron, compares with about slightly higher value in rods and cones. And at peak wavelength, he's absolutely right. You're absolutely right. It's dark at the bottom of an 800 mag rhabdome. So there seems to be no point in lengthening it. But Dan-Erik Nielsen and Thomas Labhart addressed this problem and showed that because what the long rhabdomere does is it's actually capturing the wavelengths for which inefficiently absorbed. So it's getting more photons by going out and collecting the photons for which the absorption coefficient is much less. And so you carry on getting more light, even when you could make the rhabdomere even longer. And actually their paper is really well, if you're into absorption coefficients and photopigments, their paper is well worth looking at, because they also suggested that there could be differences in the density of the pigment along the rhabdome, which meant that in fact the probability of a microvillus absorbing a photon tends to be equalized. So you have less photopigment density at the top and more at the bottom. And you can play with the rhabdomere geometry as well to try and equalize. And in fact, I'd suggested back in 1978 that light was traveling in the photoreceptors and being reflected by a tapetal sheath around each ommatidium. And they tested that, and that turned out to be wrong. But yeah.
I see. I will try to stick to the questions for now, even though I also have some of mine that I would like to ask. Next one is Toby Delbrook, and he asks, but does the method of signal to noise ratio cost in bits per second account for motion blur effects?
Yes, so that's a good point, Toby. Nice to hear that you hear from you. Yeah, so the motion blur is accounted for in the Van Hateren model by setting a photoreceptor time a phototransduction time constant. Like Van Hateren, like Hans, we used the value that was used that's been determined experimentally for fully light adapted eyes, which is off the top of my head something like 0.4 milliseconds or so. They're very fast responses. But of course, that is one of the variables. And in fact, that time constant is related to energy cost. I mean, we showed that slow photoreceptors use much less energy than fast responding photoreceptors. So the trade-off, in fact, extends from space into time, and space and time interact because temporal frequency is related to spatial frequency at constant velocity, and so on. So there's a whole area there to be looked at. Yeah, so that's a good point.
Next one up is Gregor Belusic. He has one question and one remark. So the question is, the efficiency contours only partially explain the urge for very long photoreceptors in large diurnal flyers. Could the length be explained also by its ability to prevent bleaching, for example, when looking into the sun?
Yeah, I mean, possibly. I think there are other constraints, and so I think, for example, that there's a very, so when you have a large eye, as we've seen in actually see in both holocephala, and we have a fovea in which there's a large investment of specific volume. The surface area of the eye is very large, and that's going to be a constraint for a particularly for a flying insect. And so there may be pressure to reduce the surface area by reducing facet diameter and density of facets, interomotidial angle, that you partially compensate for by having longer photoreceptors. So I mean, once you start getting away from one constraint, like the absorption curve of a photopigment, and you start considering several constraints interacting, everything quickly becomes multidimensional. And it's very easy to get lost and run around in circles. But yeah, that's a distinct possibility.
Yeah, the second one, which is a remark, and I see like it's written from Gregor Belusic, but in bracket it says Primos here. I would remark that both eye sign and IFIs in butterflies do not speak in favor of undersampling. Acceptance angles in the acute zone are 2 degrees and interomotidial angles 1.5 degrees. Would you like to comment on that?
Yeah, so there are zones in eyes which go for maximum spatial resolution by approaching the diffraction limit. There's no question about that. And again, this may be, so the problem with the virtue of, it's a bit like politicians, the virtue of using information theory is that it's relevant for everybody. But actually, it's not particularly good for specific things. so you can appeal to everybody and be bad at everything. So
without compromising.
But so I think we used information theory because we wanted a general measure. But I would urge people to start thinking about using this cost-benefit approach for specific tasks, such as the detection of a small target or the resolution of the gap through a foliage at the great distance or whatever.
The next one and the last one that I see appearing on the YouTube chat, and may I remind to people at this time that they can follow the Zoom room link that we have posted to enter this very space that we are seated in. So the last question is from Jesse S. Cost efficiency of flight is an interesting study, cost versus efficiency. What can be said about terrestrial, non-flight insects with the same estimations?
That's a very good point. Yeah. So basically, the energy costs of photoreceptors are high. And if an animal is very active in locomotion, so is the energy cost of moving around its body volume. So if you have a high field metabolic rate in an active animal, then the energy cost of the photoreceptor translates into a smaller volume than if you have a low specific metabolic rate, or field metabolic rate rather. And what that means is that the less the animal expends on locomotion, the more significant the photoreceptor energy costs become, the larger the volume of the animal they correspond to. And I've been thinking about this as to why, in a lot of large, simple eyes, the photoreceptors are actually still smaller than shorter than we predict. And one thing is that, for example, if you're a fish, then the energy cost of supporting your body and locomotion is actually much less. And that makes the relative costs of the photoreceptors much higher, so you make them shorter. Yeah.
Yeah, the constraints are absolutely intertwined. So yeah, like I would like to, as people start joining the room, I would like to ask one of my own probably naive questions. So like we are talking about photoreceptor costs, and I assume like different types of photoreceptors come with different costs. Is that right?
Yes, that is right.
So yeah. Have you tried like to make a more complex model in that regard as well, like to see how a different photoreceptor would change the trade-off between lens investment and photoreceptor length?
No, we haven't, because again, it's introducing more free parameters. So, so we haven't tried that, but we're aware that one could do that, and there probably are some very important trade-offs. And people have considered, for example, so in flies where we've assumed that the photoreceptor is basically cylindrical, it has a uniform cross section. Mm-hmm. In fact, it's known that the rhabdomeres taper. They're wider at the top and narrow at the bottom. And in fact, it was pointed out by Boschek in 1971 that this would tend to concentrate light towards the bottom. So it would tend to counteract the effects of exponential absorption. So there are all sorts of, once you start thinking.
I don't know if my connection is shaky or if all of us lost you, judging
transducers. Then you can see, you can play around with the geometry of the rhabdome in lots and lots of different ways.
Thank you very much for that. As you can see, people are already here, and we will shortly interrupt live transmission. So make sure if you want to join us in this post-talk informal get-together, given that conferences are not happening for the time being. I mean, this is the best alternative we have in our hands. I would like to thank you, Simon, once again for accepting our invitation. It was great, like definitely an honor to be hosting you. And yeah, like I would like to thank the audience as well. And as I said, make sure to join the room in case you still want to remain a part of it. So officially now I have surrendered my moderator responsibilities. People can, freely interact. Don't wait for me and the go signal.
No, he left.
Hi, Tom.
Awesome talk. I just made it for the beginning after all, so we're all good.
Tom, we didn't hear you.
Sorry, can you hear me now?
Yeah, can you repeat?
Yeah, I just said it was good to see Tom.
No, we couldn't hear Tom. I think
Oh,
Tom's
couldn't hear Tom.
connection is a bit laggy. Yeah, okay.
He's going to get his other mic. Okay.
Thank you for being.
Sorry, can you hear me now?
Yeah, can you repeat?
Yeah,
Yes.
I just said it was good to see Tom.
No, we couldn't hear Tom. I think
I couldn't hear Tom.
Okay, guys, someone probably has still the live transmission on.
Yeah, I was going to get
So
his
I
other
would
mic.
suggest you turn it off because we are getting the feedback. That is already improved, I think. Yep. Thank you.
Why such silence? Hello, Petri. Hello, Thomas.
Hey, I think now I can talk. Is that right? Can you hear me now?
Still the live transmission on. Suggest you turn it off because